customer solutions engineer at Algolia, and it's actually cool to talk just after the previous talk, because I will talk about speed of APIs, and in particular about the speed of distributed APIs, so worldwide APIs. So at Algolia, we built an API that is distributed in 12 data centers around the world. And I want to talk about the challenges that we faced and to give you some pro tips if you want to do the same thing. We think it's the future of APIs, so listen up. So first, what is Algolia? Algolia is a search API, so when you talk about search, the first thing that you think about is Google. We actually don't do the same job. Google searches for websites or web pages. We search inside websites and applications. So if you have a website and an application, you can use our API to power your search bar, your search engine. And you may have seen us already on a bunch of websites. So we are on Hacker News, on Crunchbase, on Product Hunt, and a bunch of websites around the world. And to give you a bunch of numbers, we have today more than 600 customers in, I think it's 50 countries now. We receive more than 1 billion API calls a day, and we have something like 3 billion user-generated search per month. We are not doing the same job as Google, but we have the same focus. And the focus is to have a search that is both relevant and fast. So I guess relevant, you already know what that means. When you search for Barack Obama with a typo, you don't want to go to Barcelona, even if there is the APIdays. And if you search for Britney Spears or Britney Spears or Britney Spears, actually the data is from Google. It's what people actually type. There are almost 600 ways to type Britney Spears on Google. And obviously, you don't want to find Britney Spears. So relevance, you know how it works. Performance is something that is hard, and it's the main topic of my talk today. We are actually completely crazy about speed. We have a T-shirt called Milliseconds Matter, and we believe it. So you probably know the statistics from Google and Amazon. When Google has a page that lands in 100 milliseconds more than normal, they lose 1% of the sales. Amazon's revenue is something like 80 billion a year, so that's a lot of money for 100 milliseconds. What works for websites also works for APIs and also works for search operations. So to understand what I mean by that, let's look at a typical search, a regular search we see on most websites today. So you type iPhone blue, 5C, 16 gigabytes. It takes approximately 9 seconds. Then you have something like 1 second to ping the server, get the processing done, and get the answer back. Generally, you have to load a new page to do that. And then you select the result. So the question is, how do you improve the speed of the whole process? First thing you have to do is have a better relevance, because you want to find what you want to find, and you don't want to have to make another search to find the object you were looking for. So first thing is relevance. The second thing is pure speed. So if you want to look for an iPhone, you can just type IPH and have an iPhone. You don't need to type everything. So if you do that, then you have this kind of graph. So you type one letter, and you have an answer automatically, very fast. And you have, when you type P, you have another answer. And when you type IPH, you already have all the iPhones displayed on your page. And this is the user experience time. And it's only possible if you can provide an answer that's between two keystrokes of the user. So the technical API time is really important because it actually changes the whole experience for the user. So this will explain most of the choices we made. First thing, we built an engine from the ground up. We wanted to have software that was designed for speed and relevance. Actually, the company started off as a mobile SDK. So the idea was to make an offline search for mobile applications. And when you do that, when you build an engine that works on a mobile with no network, no CPU, and very few amount of memory, you have to optimize a lot of things. And the technical project was successful, but the business project wasn't. And since we changed now from an offline SDK to big data centers with a SaaS product, we have like almost an unfair competitive advantage because the software is really optimized for speed. Second thing you have to do is to optimize the hardware. We actually put a really long time searching for the best servers for what we are doing. And most of the SSDs that we've tried were too slow and were burned after 2 months. Also, you have to have specific settings on your servers to work for you. So, for example, most Linux distributions actually are optimized for hard drives and not SSDs. So we had to make a lot of kernel configurations to make sure that the hardware matches what we want to do with the software. And then the third thing, which matters a lot today, is to optimize the network. So as you said as you've seen in one of the previous slides, the latency of search takes a lot of time. So once you have a processing time that's fast, you need to improve the latency. So the first thing was we wanted to be as close as possible to our users. And that meant having a search that goes directly from the front end to our servers and that is closed physically to the customers, to the users of the websites we are providing the search for. The way it works is we have a set of 12 data centers around the world, and when a website decides to index his data on our servers, we actually can replicate it to other data centers around the world. And just so you know, it's not a CDN, it's not a cache system. It's a real 100% replication of the engine itself. So the data and the engine, everything is duplicated. And when you have that, when a customer actually makes a search on the website or an application, you can give the answer from the data center that is close to him. So everyone can have a low latency. And now I want to give you 8 tips on how to do that. Building a distributed API is something hard to do. It took us a long time. And if you want to do it, these tips will help you. First tip, logistics. AWS is only in 6 locations in the world, I think right now. So if you want to have 12 data centers, you want to have more providers. There is no ideal worldwide provider. Actually, in our case, we have specific hardware, so it was what we wanted to have wasn't on AWS. And you have to anticipate that the data centers don't work the same way in all countries. For example, in our Singapore data center, we actually we have to take 3 months to have a server delivered, which takes, I don't know, a few hours or a few days in Europe or in the US. So first point was logistics. Second thing is pricing. Pricing is very different from country to country. For example, when you buy a server in Brazil, there is a 15% tax on the servers. So the price will be very different. You can double it when you go to Asia and triple it when you go to South America or South Africa. We're actually building our 13th data center in Johannesburg right now, in South Africa. Then you have the question, do I update my business model on different regions, or do I want to handle this on my side and have the simplicity of one pricing? That's the choice we made. Third thing, which is really the most complicated part actually, is how will you replicate the data from one data center to another? And the basic way to think about it is to say, I will take my 12 data centers and sync them around the world. And it's really hard to do because you have a lot of latency between all the data centers. So we tried multiple approaches, and the one that works best is a simple one. You have to stay simple if you want to do that. So what we decided to do was you have one master data center per customer, and this data center is responsible for one-to-one synchronization with all the others. So you don't have a worldwide synchronization. So keep it simple. Number 4, DNS. DNS is the way we thought would work to find the closest data center. And it works in some cases, but not in all cases. For example, some of our customers decided not to have the 12 data centers, but only to have 8 of them. And if you do that, then you cannot have a route that works for all customers. So you have to program the route depending on the customers. And you can do that with, you cannot do that with Amazon Route 53. You can do it with NS1. So we think it's EDNS is a big plus, and you should absolutely use that. Point number 5, which I think is funny, we fell into the trap of thinking .io was cool. It is cool, it's just slow. It's something you have to think about. I think there is something like 6 or 8 central servers for .io when you have 200 servers for .com or .net or .org. So you want to be cool, but you will be fast if you have a .com. 6, peering. So peering, for those of you who don't know, is the preferred path, the preferred route for the data, depending on the agreements your provider has. To give you an example, when we had a customer from Australia that wanted to talk to our data center in Singapore, the path taken by the data was you go to Japan, and then you go to Hong Kong, and then you go to Singapore, which takes something like 150 milliseconds. And this was because of the writing our Singapore provider had with Japan. And your providers most likely won't change the peering for you. So if they don't change it for you, we advise you to change providers because it matters a lot. And in your case, when we changed, we went from 150 milliseconds to something like 40 milliseconds. So it makes a huge difference. Point number 7, again, a mistake we made was to think that monitoring is simple. You just pay for a service that makes the monitoring. The problem with that is you cannot program the operations you want for the monitoring, and you cannot really decide the location from which the servers will be pinged. And so we decided to build our own monitoring system, and actually it's pretty simple. We have 13 providers that gave us 45 servers around the world, and it costs nothing, something like $500 a month. And you can configure them because they are your servers. So you can make them test for if a server is down, but you can also test more complex operations. For example, we try all the API operations directly from our monitoring system, and we monitor the time it takes, so we can know everything about how our servers work very simply. And when you begin to have, I don't know, maybe the limit is 100 servers, then you have hardware failures all the time. So it's really important to monitor it well. So that was the point 7. And the number 8, the last one, the failover. So as I said before, DNS is a good solution to make sure the data center is hit by the search query. The problem is most providers around the world actually don't respect the TTL. So if your server is down and you have the TTL set at 1 minute, then normally after 1 minute, the request will be redirected. Actually, most providers don't read the TTL, so they put limits that is sometimes 1 hour, sometimes 2 hours, sometimes a day. So your server will be down for 1 day for them. So the solution we found was to have a fallback strategy directly implemented in our API clients so that when the DNS doesn't work, we have a solution that will hit another server when a server is down. That was the 8 tips. Building a distributed API was something really hard. It took a long time. But we went to a solution where we have a latency time of under 100 milliseconds in almost all the world for all of our customers. And we think it matters. We think the future of API is distributed. And thank you.
Thank you very much. Time for a few questions. Yeah, 2 questions.
Hi. I'd like to know, I was astonished by the difference you mentioned in speed between IO domain names and .NET domain names. Like, how big is the difference? Can you measure that?
Yeah. It really depends on the location you are and on the location of the central servers. And you are not supposed to know the location of the central servers. But it can be tens of milliseconds.
Tens of milliseconds?
Yeah.
Like,
in the worst cases, yeah.
Like, what does cause the difference?
Tens of milliseconds of difference between...
Yeah, like what's the reason for it?
The reason is for .io you have only 6 central servers that will give you the good route, the good DNS route. In .com or .net you have 200 around the world. So you are closer to the central server.
Okay, and is the difference just if you're in Japan or in Africa, or is it the same in Western Europe and US?
Actually, we are not supposed to know the location of the central servers, but you can obviously find them. And most of Europe and US is okay. When you go to emerging countries mainly, it's way slower.
Thank you very much for your talk. It was really interesting. Now, personally, I've experienced one of the most difficult problems to solve when it comes to performance is tackling the outliers. And I would like to know about your experience. For example, everything is good when you think about, in terms of average, but then you tend to have, for example, 1%, 2%, 5%, and they go above a certain threshold.
Yeah.
So what is your experience and how did you tackle that?
Yeah. So one thing that is obviously important, and not everybody does it, and is to not only measure the average time. So for all our customers, what we actually do is in their dashboard, they can find the average time, but also the 99% time. And it's something we measure as well, because we think if only one query is too slow, it's already a bad thing. And you actually have to really go deep into your logs to understand what happens. So for example, one of the things we found was sometimes one of our servers would put a very long time to answer. And so what we initially thought was there was latency, and it wasn't. So after investigation, we actually found that the configuration of our kernel said that 10% of the data can be cached into the RAM. But in our machines, we have 128 gigabytes of RAM. So that's a lot of RAM. So in the worst case scenario, 13 gigabytes of RAM will be flushed instantly to the SSD. And when you do that, obviously, 13 gigabytes is a lot of data for SSD, so everything was slow for a minute. So if you don't investigate the edge cases, you won't find the problems. Yeah.
We have time for one last question. Here.
So you mentioned rolling your own monitoring services.
Yeah.
How many people do you employ to do that?
We are actually 20 in the company. I think 5 months ago we were 10, so not that much.
Okay, so, sorry, 10 people just to do the monitoring stuff?
In everything.
As a whole?
Yeah.
Right.
I think it took us 1 week to build the monitoring system, actually.
Gotcha.
So it's kind of fast to do.
And
You just have to have 45 data centers and to run a script on each of them.
Right. My real question here is, like, at what point would you make the decision how to turn basically the return on investment when it comes to that developer time?
Yeah. It's actually simple to do. We thought it would be hard. It's not that hard to build. What was the turning point for us was we want to track operations that we cannot track with existing monitoring systems. So for example, we wanted to track the indexing process if it worked. And even there are some programmable monitoring systems, but this kind of operation was tough to do for us. So it was a turning point. And I think it's a good reason to build your own monitoring system.
Okay. Thank you very much, Nicolas. Thank you.
you.